Energy is what we're talking about now, but it's not an entirely new topic. We still have to keep thinking about Newton's laws and acceleration. Energy is a somewhat difficult idea to define. For our purposes, let's just say that energy is something that has to be present to make any natural process happen. That you can't move anything without using energy. You can't move electric current through a light bulb without using energy. You don't move your car without using energy, and so forth. But in any of those processes that need energy, energy gets moved around. Energy always gets moved around during that process from one thing to another thing, or it's transformed from one type of energy to a different type of energy. One of the ways in which energy can get moved around is heat, in which energy flows from things at high temperatures to things at lower temperatures. But what we'll be focusing on is another way to move energy around called work. Work is a way to move energy around, and it involves forces and movement. And the basic idea of work is simply this. The total energy change experienced by an object or by a system of many objects is just equal to the work done by the net force, or what amounts to the same thing, the total, the sum of the work done by every individual force. But it's easier just to say this is the work done by the net force. And I'll be using W with subscripts often. W without a subscript just always means the net work on an object or the net work on a system done by the net force. And this equation tells you, among other things, that the numerical value of work is just equal to the amount of energy change that object or that system experiences. Positive work means the change in energy is positive. Energy is gained by the object or system. Negative work means energy is taken away from the object, taken away from the system. A negative energy change. And then, of course, zero work means no change in the system's energy or no change in the object's energy. So, the numerical value of work is important. How do you calculate that? With this, you do it with this equation here. This is actually an equation that works for a somewhat simplified case, a case where there's a constant force. But what are the factors here? The magnitude of the force times the magnitude of a displacement vector. Right? The object that's having work done on it is feeling the force while it's moving. And then when thinking about work, the important part of that movement is the displacement. And then cosine of theta, where theta is just the angle between the displacement direction. Let's say the thing starts here and ends here, so the displacement vector always points from the starting point directly at and points directly to the finishing point. And this angle theta is the angle between the displacement direction and the force direction. So just to take a simple example, let's say we have a ball rolling down a hill. There's the hill, there's the ball, and so the displacement of the ball is just a vector that points straight downhill. The ball starts here, and then a little bit later the ball is here. So there's the displacement. And while that ball is rolling, it feels some forces. Of course, it feels the weight force, the gravitational force from the Earth, which is always pointing straight down. And I'll refer to weight as mg rather than w, because now I'm using W for work. And then there's a normal force from the hill pushing on the ball. Normal force is always perpendicular to the surface that's doing the pushing. So the normal force points that way. And the ball is rolling downhill rather than sliding downhill. It's not sliding in this direction. So anytime sliding could have happened, but it's being prevented, that's because there's some kind of friction force to prevent the sliding. And in this case, it makes the ball roll instead of slide, so that friction force is rolling friction. And the slide would have been this way in the downhill direction, but any friction force that prevents sliding does so by pointing opposite to the slide. So the rolling friction force points straight uphill. Now, what can we say about the work done by each of those forces? Start with the work done by the normal force. Subscript N here just means that I'm not talking about a net force any longer. I'm just talking about the work done by this one force, the normal force. And so that work is what? It's just the magnitude of the normal force, whatever that might be, times the magnitude of the displacement, which in this case would just be the distance between the starting point and wherever the ball ends up. And we'll just call that D, times the cosine factor, and cosine of the angle between the force direction and the displacement direction. Well, the displacement points straight downhill. The normal force is perpendicular to the hill. If the displacement points along, parallel to this surface, and the normal force, like any normal force, points perpendicular to the surface. So so that cosine factor is cosine of 90 degrees. And trigonometry tells us that the cosine of 90 degrees is 0. So that force actually does no work. In other words, that force doesn't do anything to change the energy of the ball. On the other hand, what about the work done by weight? Work done by the weight is, again, just the magnitude of the force, magnitude of the weight, m times g, whatever that might be in this case, times the magnitude of the displacement, well, just the distance between the starting point and the finishing point, times cosine of the angle between the displacement direction and the force direction. And the displacement direction is straight downhill. And in this case, the weight force is straight down, so that's the angle. We don't know exactly the numerical value of that angle, but we do know that it's some angle greater than 0 and less than 90. Right? These two directions are not the same direction, so the angle between them is not 0, and they're not perpendicular to each other. The angle is not 90 degrees. Some angle greater than 0, less than 90 degrees. Trigonometry tells us that any angle like this must have a positive value for the cosine. So the work done by the weight is a positive work, and whenever you have positive work, that's a positive contribution to the total energy, a positive delta E, an increase in the total energy. And then finally, what about the work done by the rolling friction force? just like the other two cases, it's the magnitude of the force times the size of the displacement times cosine. And that, as always, that's cosine of the angle between the displacement direction and the force direction. The displacement direction is straight downhill. The rolling friction points opposite to that, straight uphill. So the angle between displacement direction and force direction is 180 degrees. They're exactly opposite to each other. Trigonometry tells us that the cosine of 180 degrees is -1. So the work done by the friction force is just -1 times the magnitude of the force, which is always positive. Right? This is a magnitude, size, strength, absolute value. Just by our definition of size, strength, and absolute value, that must be a positive number. Likewise, this is the magnitude, the size, the strength of the displacement vector. And any magnitude, size, displacement, size, or absolute value must be a positive number for this displacement vector. So these are both positive numbers times -1. That's definitely a negative number. Work done by the rolling friction is negative. That is, it causes a negative change, a decrease in the system's total energy. Takes energy away from the ball in this case. Now let's look at a simple example, even somewhat simpler than the one I drew before when explaining what the different terms here meant. Let's say here's the starting point for something. Here's where the thing ends its motion, so the displacement vector points that way. And let's say that it feels a constant force in the same direction. And not just any force, let's say that the net force is pointing in that same direction. Okay, so then the work done by this is the kind of work that we always refer to as just plain W, and that will tell us exactly what the energy change is for the thing that's feeling that net force. So what is that work? It's just the magnitude of the net force times the magnitude of this displacement. And the magnitude of any displacement is just the distance between the starting point and the finishing point. We'll call that distance d, times cosine of the angle between the force direction and the displacement direction. They're both in exactly the same direction. So the angle between force direction and displacement direction is 0 degrees. So we've got cosine of 0 degrees. Trigonometry tells us that the cosine of 0 degrees is +1. So that's just a distance, which is, by definition of distance, a positive number. This is a magnitude, a size, or an absolute value of force, so that's a positive number. And of course there's a positive number as well, so the work done by the net force in this case is positive work. The thing's energy, the thing that feels this net force, has an increase in its total energy. There are different types of energy. So specifically, the change in energy is positive. there are different types of energy, so specifically, to be more precise, which type of energy has increased? Let's look at this in a little bit more detail. We can rewrite magnitude of net force, just use Newton's second law. Force equals mass times acceleration, so magnitude of net force is just equal to mass times magnitude of acceleration. So let's write it that way. Mass times magnitude of acceleration times distance, distance between the starting point and the finishing point. Now, let's just define the direction of motion to be positive, as we almost always do, which means the net force was pointing in the positive direction, and Newton's second law tells us that the acceleration points in the same direction as the net force. So the acceleration points in the positive direction. So actually we can get rid of this absolute value sign. The acceleration actually is a positive number in itself. So we just say that A is the numerical value, whatever it is, of the acceleration. A must be positive because the net force that caused it points in the positive direction. All right, now go way back to chapter 2 when we were thinking about those kinematic equations and problem solving. One of the kinematic equations we saw was this one. Final velocity squared equals initial velocity squared plus 2 acceleration times the difference between the initial location and the final location. Now in this simple case, we're just assuming that the object moves along a straight line from the initial location to the final location. So that would make this difference here, the difference between the final location and the initial location, just the same as the distance traveled between the start and the finish. In other words, just the same as d. So what this equation really tells us is that final velocity squared equals initial velocity squared plus 2ad. Rewrite that just a little bit. Final velocity squared minus initial velocity squared equals 2ad, or divide both sides of that equation by 2. And we've got final velocity squared minus initial velocity squared divided by 2 equals ad. There's ad up in our algebraic expression for work. So let's rewrite work by writing ad this way. So AD is just the difference between the square velocities, final velocity squared minus initial velocity squared, over 2. Or rewrite this a little bit, 1/2 mass final velocity squared, 1/2 mass final velocity squared minus 1/2 mass initial velocity squared. That's the work done on this object that was feeling that net force. And at this point, we define a particular type of energy called kinetic energy, and we symbolize that just with a uppercase K. Kinetic energy of an object is defined as 1/2 times its mass times its speed squared. So that expression there is just the final value of kinetic energy, 1/2 mass times final velocity squared. And that number there is just the initial kinetic energy. So the moral of the story is, in this particular case, the work done by the net force on that one object is equal to final kinetic minus initial kinetic energy, which is just what we mean when we use this symbol delta K. Change in anything is just the final value minus the initial value. So in this case, in this particular case, where we're talking about the net work done on just one object, think of it as a system containing just one object. The energy change of that one object system is just a change in its kinetic energy. When we get systems that contain larger numbers of objects, more than just one, there'll be more than just one type of energy. And in that case, the work done by the net force could change the kinetic energy of the different objects and change other kinds of energy. But if our system is just this one object, kinetic energy is the only kind of energy there is. It's the only kind of energy that can change when work is done by the net force. Let's look at this in just a little bit more detail. So, go back to our definition, our defining equation for work. Work is just the magnitude of the net force that's acting on the object times the magnitude of the displacement that the object has while it's feeling that net force, times cosine of the angle between the displacement direction and the force direction. And in this simple case that we're considering here, the displacement and the force point the same way. So the angle between displacement and force is 0 degrees. Cosine of 0 is just plain 1. So that's work. And it's going to equal the change in kinetic energy. So now imagine two cars, both starting in their initial locations, starting at 0 velocity, starting from rest. And then they both travel the same distance. They both go through the same displacement, d. And while they're moving through that same displacement, they both feel the same net force. So they both feel the same net force, and they've traveled the same distance. But let's say that one of those cars is much more massive than the other. Car 2 has a much bigger mass than car 1. But they both travel the same distance and feel the same force while traveling that same distance. So net force is the same for both of them. The size of their displacement, the magnitude of their displacement is the same for both of them. So they both have the same change in kinetic energy. same force over the same distance, and they're both traveling in the same direction. And so that means the same amount of work is done on both of them. The same amount of positive work is done on both of them. This is a positive number because this is a magnitude, which is positive by definition of magnitude. This is a magnitude, so it must be positive. So they have the same work done, same change in kinetic energy, but that change in kinetic energy is, of course, the final 1/2 mass final velocity squared minus the initial 1/2 mass initial velocity squared, but they both started from rest. They both started from 0 initial velocity, so that term is just plain 0. So they both end up with the same amount of kinetic energy. So car 1's final kinetic energy is equal to car 2's final kinetic energy. 1/2 mass 1 car 1's final velocity squared equals 1/2 mass 2 car 2's final velocity squared. So even though they end up with the same amount of kinetic energy, they'll of course end up with different velocities because car 2 has a bigger mass than car 1. This factor is bigger than this factor. So in order to make both sides of the equation equal, if this thing is bigger than this thing, then this thing has to be smaller than this thing. The first car speeds up more, the first car accelerated more, and so ends up at a higher speed. And that's not surprising. That's exactly what we would expect, even if we weren't thinking at all about energy. If we were thinking just about Newton's second law, acceleration equals net force divided by mass. They both feel the same net force. So when we're comparing 1's acceleration to 2's acceleration, this factor is the same. The numerator of this fraction is the same for both cars. So the bigger mass, for the bigger mass, this fraction will be smaller, less acceleration. The bigger car gets less acceleration. The car with the smaller mass, the smaller denominator, makes a bigger fraction, makes a bigger acceleration. Exactly as we would expect. The car with less mass, that means it has less inertia, so it's easier to accelerate. So when you apply the same force to two different things, the thing with less mass, less inertia accelerates more, it ends up at a higher final speed. Okay, that's just to say that the result we get from thinking about energy is consistent. It's the same as the result we'd get by thinking about Newton's laws. And one last thing about energy, you have to be able to think about proportionalities when talking about energy. So kinetic energy looks like that, 1/2 mass velocity squared. If we're talking about just one object and looking at how its speed changes as time goes by, then of course, since we're always looking at the same object, that mass factor is constant. So what we have here is kinetic energy equal to constant factors times a variable, v squared. That's the general algebraic form for direct proportionality. One variable equals a constant times another variable. And then direct proportionality means when one variable changes by some factor, the other variable must change by the same factor. The only trick in this case is to remember that one of these variables is kinetic energy. The other variable is v squared, not v. Remember, this equation tells us that everything that isn't a constant factor is the variable. And in this equation, everything that isn't the constant factor isn't v, it's v times v. So, kinetic energy is directly proportional to velocity squared. That means, however velocity squared changes, kinetic energy changes exactly the same way. So let's say we've got a car and it's moving at a certain speed so that its kinetic energy is 5,000 joules. And that happens when it's moving at a particular speed that we'll call v1. Now, how much energy does it have if the speed doubles? So now a new speed, v2, is just twice v1, and in that case, what is kinetic energy 2? What is the new kinetic energy? Absolutely do not jump to a conclusion and say that the velocity doubled, so the kinetic energy doubled. No, 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 no. Think through and use what you know. And what you know is that there's direct proportionality between kinetic energy and velocity squared. So however velocity squared changes, that's how kinetic energy changes. Or to be a little bit more precise, when velocity squared changes by some factor, kinetic energy changes by the same factor. So we need to know how velocity squared changes. We need to know the factor by which velocity squared changes. Well, here's how velocity itself, velocity to the first power changes, so we can easily see how velocity squared changes just by squaring this equation. Square the left-hand side, we've got velocity 2 squared, and whatever we do to one side of an equation, we have to do it to the other side of the equation to keep both sides equal. So square this and we have 4v1 squared. So we can see that the variable called v squared, here's the old value of v squared, v1 squared, here's the new value of v squared, v2 squared, and the new value of v squared is 4 times the old value of v1 squared. The variable called v squared changed by a factor of 4. So anything that v squared is proportional to also changes by a factor of 4, like kinetic energy, for example. The new kinetic energy is 4 times the old kinetic energy, and that would be 20,000. 20,000 joules. The kinetic energy does not double to 10,000 joules, it quadruples to 20,000 joules, because the kinetic energy is not proportional to velocity, it's proportional to velocity squared. And then just one more example like that, sort of doing it the opposite way. We still need to use this fact that kinetic energy is proportional to v squared. They change the same way when they both change by the same factor whenever there is any change. So let's say that at one value of kinetic energy, the velocity is 10 meters per second. And then the question is, how much do you have to speed up to get twice as much kinetic energy? How much do you have to speed up to double the kinetic energy? So when the new kinetic energy is twice the old kinetic energy, sorry, that's original velocity. So when kinetic energy has doubled, what is the new higher speed? And don't jump to the conclusion and say that it's just twice the old speed. No, no, no. That would be true if kinetic energy were proportional to velocity itself, but it's not proportional to velocity itself. Go back and stop, slow down, use what you know. Kinetic energy is directly proportional to velocity squared, so kinetic energy changes the same way as velocity squared. When kinetic energy changes by some factor, velocity squared changes by the same factor. In this case, kinetic energy changed by a factor of 2, so velocity squared changes by a factor of 2. The new velocity squared is 2 times the old velocity squared. But what we're looking for, of course, is the new velocity itself, the new velocity to the first power, v2 to the first power. But we can get v2 to the first power just by taking the square root of this. And of course we have to take the square root of the other side of the equation to keep both sides equal. So this implies that the square root of this, plain old v2, equals the square root of this, which is square root of 2 times the square root of v1 squared. And then v1 was 10. Square root of 2 is roughly 1.4. So the new velocity is 10 times 1.4, 14 meters per second. The velocity does not have to double in order to make the total kinetic energy double, because kinetic energy behaves the same way as v squared. It does not behave the same way as v. Okay, that's enough to chew on. Now you can try the after lecture exercise.